The process begins with the preparation of a large model representing the base structure to be cast. This model, made at Neri, is divided into two main parts to facilitate handling and molding. Before the molding process begins, the model is coated with a special release agent. This coating ensures that the mold can be separated from the model without causing damage to the intricate details of the imprint. Once prepared, the model is placed inside a large steel molding box. This box is then filled with a specially formulated resin-bonded sand. As the sand hardens, it captures the precise shape and contours of the model. The operators also press the name of the client into the surface of the sand, providing a means of identification for the mold. The sand requires approximately 10 minutes to fully cure and harden. After hardening, the box containing the negative impression of the model is lifted. Certain components of the model are manually removed with care to avoid compromising the shape of the mold. Next, the sand mold is treated with an iron oxide coating. This coating plays an important role in improving the surface finish of the final cast product. Once applied, the coating is dried in an industrial oven to ensure it adheres evenly. The two mold halves are then positioned side by side. Into the bottom half, the core is placed. This core is essential in forming the internal cavity of the cast component. It is slightly smaller than the desired cavity by about 1 centimeter on all sides, which determines the final wall thickness of the cast iron part. Placing the core correctly is a delicate and precise task. Alignment pins are used to guide and facilitate the accurate positioning of the two mold halves, ensuring a perfect fit during the closing of the mold. Meanwhile, cast iron is melted in an 18-ton oxy-combustion rotary furnace. The process of melting the metal to reach the required temperature of 1,500 degrees Celsius takes approximately 2 hours. During melting, impurities rise to the surface as slag and are skimmed off to improve the purity of the molten metal. A temperature probe is used to ensure that the iron reaches and maintains the optimal pouring temperature. Once the molten iron is ready, it is poured into the prepared mold cavity. The heat and pressure fill every part of the mold, including the voids left by the core. The following day, a large mechanical arm removes the sand mold from around the cooled casting in a process called demolding. At this point, the solidified cast piece is freed from the surrounding sand. The surface cleaning of the casting is carried out inside a shot blasting machine. Here, small steel balls are projected at high speed onto the surface of the casting. This abrasive action cleans the surface by removing any remaining sand particles and scale. After several minutes in the shot blaster, the cast iron part emerges with a clean and smooth surface. The last step in the process is the removal of flash and excess material left from the casting seams. These are carefully trimmed and ground away to ensure the final component meets the required specifications and surface finish. Through this complex and meticulously controlled process, from the initial model to the final cleaned casting, the foundry transforms raw materials and designs into high-quality cast iron components. The process begins with melting sorted scrap steel in an electric arc furnace, producing up to 50 tons of liquid steel per heat. After tapping, alloy refinement and purging are carried out in a ladle furnace, followed by vacuum degassing. The refined steel is bottom poured into square or rectangular ingots. Electroslag remelting may be used to enhance purity and homogeneity. Ingots are heated to 1,200 degrees Celsius before forging on a 60 meganewtons press. Forgings are then flame-cut and heat-treated in bogey hearth furnaces. Oil and water quenching tanks ensure consistency. After milling, hardness and ultrasonic tests are performed. Additional mechanical tests follow before preservation, identification, and shipment of the forged steel bars. The 5-axis milling process on the Herco VMX60 begins with importing the solid model and setting up the engine block on the large 66 by 26-inch rotary table. With 60 by 26 by 24-inch travel and a 12,000 RPM spindle delivering 87 feet lbs of torque at 2,900 RPM, the machine performs trochoidal pocket milling and rest material machining efficiently. Simultaneous 5-axis movement allows for deep hole drilling with a 40 mm solid drill and spiral plunging for smooth entry. The swivel head enables complex machining of cylinder side surfaces and angled features. Chamfer rolling is used to create beveled edges, and text is engraved precisely onto the part. With a 40-tool CAT40 capacity and 20,000 pounds weight, the machine ensures stability and high precision. The process ends with adaptive tool paths and fine finishing for optimal surface quality. ZF Wind Power provides comprehensive gearbox services throughout the entire product lifecycle. The process begins with inbound inspection of gearboxes from wind turbines ranging from 0.8 to 9.5 megawatts. Components are disassembled and undergo detailed gear and housing measurements. Gears and planet carriers are reworked, and castings such as housings are also repaired and reworked. The service includes solutions for repairs and upgrades, ensuring components meet high-performance standards. The company performs both up-tower and on-site repairs, as well as workshop-based repairs. If necessary, replacement units are provided. After reassembly, each gearbox undergoes a test run to verify functionality. The units are then painted, followed by a thorough outbound inspection. Finally, the serviced gearboxes are delivered back to the customer, ensuring high reliability and customer satisfaction across ZF and multi-brand gearboxes globally. Additionally, the use of a Siemens motor enhances the reliability and energy efficiency of the entire system. Once cutting is complete, the chunks are removed manually or through a conveyor system, depending on the plant layout. The machine is then ready for the next tire, ensuring continuous and efficient operation. Forgiatura Morandini, based in Cividate Communo, Italy, specializes in open die forging with an annual production capacity of 75,000 tons. The company forges pieces ranging from 100 kilograms to 250 tons, with diameters up to 6,500 millimeters and lengths up to 23,000 millimeters. Raw materials, primarily vacuum degassed steel ingots, are heated in 13 furnaces, 9 stationary and 4 movable, handling loads up to 300 tons. Forging is performed using presses rated at 1,000 T, 3,000 T, 2 units, 7,000 T, and 16,000 T, supported by manipulators with capacities from 3 to 300 tons. For rings, a hot rolling plant produces parts up to 8,000 millimeters in diameter and 150,000 kilogram. Physical, chemical, and metallurgical parameters are tightly controlled to meet the stringent standards of nuclear, petrochemical, naval, and energy industries. Schmiedewerke specializes in forged products for the mechanical and plant engineering industry, operating an electric arc furnace that produces up to 50 tons of liquid steel per load. The process starts with 100% sorted scrap, melted and tapped, followed by precise temperature and alloy adjustments in the ladle furnace. In the VD or VOD units, dissolved gases are removed to ensure material purity. After a purification rinse, the molten mass is cast into forging blocks optimized in weight and size. The largest ingots weigh up to 76 tons, formed from 2 heats. If higher purity and homogeneity are needed, electroslag remelting is integrated before forging. Ingots are heated to 1,200 degrees Celsius and forged using a 60 meganewton press, supported by powerful manipulators. Power generation forgings like turbine shafts are upsetted after pre-forging for ideal material properties. For smaller forgings up to 20 tons, a 27 meganewtons press is used. Post-forging, parts undergo heat treatment in calibrated bogey hearth furnaces and are quenched in temperature-controlled oil or water tanks with high circulation capacity. For components up to 8.5 meters in height requiring high concentricity, vertical heat treatment is available. After heat treatment, forgings are machined. Test rings are removed, and samples are taken for tensile, impact, structure, and purity tests. Ultrasonic inspections are performed either manually or through automated systems. Final steps include preservation, marking, and thorough inspection before delivery authorization and dispatch to customers. Inside a modern melt shop, steel is produced through an intense and carefully controlled process using electric arc furnaces, EAFs. Each furnace can produce up to 50 tons of liquid steel per heat, operating at temperatures reaching 1,800 degrees Celsius. The process starts with charging the furnace. Carefully sorted and layered scrap metal is placed into the furnace buckets to optimize melting efficiency and protect furnace linings. High-voltage electric arcs delivered through graphite electrodes initiate the melting process, which typically takes around 37 minutes. As the scrap melts, refining begins. Slag is formed to trap impurities while oxygen is injected to remove excess carbon, phosphorus, and other unwanted elements. Alloying materials may also be added to meet precise steel specifications depending on the final product's requirements. Once the steel reaches the correct chemical composition and temperature, the furnace tilts to tap the molten metal into preheated ladles. From there, the molten steel is transported to continuous casting machines or molds, where it solidifies into billets, blooms, or slabs. Environmental responsibility is central to modern melt shop operations. Advanced gas cleaning systems capture dust and emissions, ensuring compliance with stringent environmental standards. Using recycled scrap as raw material significantly reduces the carbon footprint compared to traditional blast furnaces. This combination of precision, power, and environmental consciousness enables melt shops to produce high-quality steel products for industries worldwide. From construction to automotive manufacturing, ensuring that the tradition of steelmaking evolves with modern technological and sustainability demands. The production of Mira marble mosaics begins with the selection of high-quality marble blocks which are cut into slabs using gang saws. These slabs are then transferred to the processing line where they are trimmed into smaller pieces suitable for mosaic production. The cut pieces undergo surface treatment, such as honing or polishing, to achieve the desired finish. Next, skilled workers carefully assemble the pieces into specific mosaic patterns on mesh backings, ensuring precision in alignment and design. These sheets are then fixed using adhesive and passed through a pressing and drying stage to secure the mosaic tiles. After quality control checks, the completed mosaic sheets are packaged and prepared for shipment. Throughout the process, both manual craftsmanship and automated systems are used to maintain consistency and meet aesthetic standards. This integrated approach allows Mira Marble to produce a wide range of decorative mosaic designs with high precision and quality. The assembly of the Menk MHU 3500S hydraulic hammer commenced with the precise installation of a 6.5-meter anvil into the upper and lower segments of the pile sleeve at the quayside. Subsequently, the 257-ton pile sleeve was lifted into the cargo hold of MV Trina using the ship's heavy lift cranes. The hammer was then upended and mounted vertically onto the pile sleeve with high positional accuracy. This alignment was critical for securing the hammer foot via 90 heavy-duty foundation bolts. The onboard cranes were employed for the entire assembly operation, ensuring structural integrity and minimizing mobilization time. Upon completion, the fully integrated hammer unit was sea-fastened for transport and later discharged as a single piece for offshore deployment. The Iscar-Cham IQ drill cartridge tool operates by mounting indexable carbide inserts onto replaceable drill heads, allowing high-efficiency deep-hole drilling. During operation, the outer and inner inserts cut simultaneously, ensuring chip evacuation through internal coolant channels. The tool maintains excellent concentricity and straightness, even in long drilling applications. With a diameter range of 33 to 65 mm and lengths up to 12 times d, it achieves cutting speeds up to 180 meters per minute, depending on material. Its modular design allows rapid head indexing or replacement without removing the body, minimizing downtime and enhancing productivity in heavy-duty drilling applications. Steelmaking at ThyssenKrupp CSA Brazil begins in the 330-ton LD/BOF converter, where molten iron is refined into steel through oxygen blowing. This process removes carbon and impurities with high efficiency, ensuring optimized steel production. The LiquiRob system enhances converter performance by enabling reliable, automated operation and monitoring of emissions. After refining, the molten steel undergoes precise heat treatment in the aluminum heating furnace to achieve the desired temperature and consistency. The steel is then transferred to the continuous casting stage, where it is poured into a cassette-type mold system that offers flexibility and accuracy. To ensure excellent surface quality, the casting process employs the Dynaflex technology, which dynamically adjusts mold oscillation and cooling parameters. This integration of advanced systems guarantees consistent quality and high productivity throughout the steelmaking process. Manufacturing process of metal building systems. The process begins with computer-aided design, where engineers input structural data to generate precise fabrication drawings. Steel coils arrive at the factory, sorted by function: structural frames, purlins, girts, or pre-painted panels. The steel is straightened and cut using plasma cutters to form flanges and webs, which are then welded into frames by automated machines. Lighter coils are roll-formed into purlins and girts. Pre-painted coils are shaped into roof and wall panels with durable, aesthetic profiles. All components, frames, panels, and accessories are loaded for delivery to the construction site. On-site, authorized builders assemble the system efficiently. This integrated process ensures rapid construction, material optimization, and high environmental sustainability, revolutionizing low-rise commercial building. The production of generator shafts at Saarschmiede begins in the heart of their electric steel plant, where molten steel is prepared for casting. The steel, melted in an electric arc furnace, reaches temperatures exceeding 1,700 degrees Celsius. Once it reaches the desired heat, the glowing steel is tapped into a ladle. The precise alloy composition is proprietary. From the ladle, the liquid steel flows directly into a mold to form a massive ingot weighing up to 80 tons. After solidification, the raw ingot is transferred to a gigantic reheat furnace called the Herd-Wagen-Ofen to regain the necessary forging temperature. These furnaces consume as much heating gas per day as a small town. Handling such heavy and hot material requires extreme precision. Once the steel block reaches the appropriate temperature, it is moved to the world's most modern open-die forging press, where the main forging steps begin. The first step is to create a gripping pin zapfin to enable easier handling of the piece. The forging team then starts the reckon or elongation process. Using a press with up to 7 tons of pressure, the red-hot ingot is stretched to a specific length. The operators carefully measure throughout the process to ensure dimensional accuracy, typically within 2 meters. As the outer scale cracks off under pressure, compressed air is used to clean the surface. Pressing not only reshapes the block but also improves internal grain structure, much like kneading dough. If the temperature drops below the optimal range, the workpiece is returned to the furnace before continuing. For the next step, the forging dies, or satelle, are exchanged to accommodate the next shaping stage. The workpiece is now pressed and guided between these saddle dies with controlled pressure, unlike traditional hammer forging offering a more refined shaping method. This cycle of reheating and pressing is repeated multiple times. Each round enhances the density and mechanical properties of the steel, which is crucial for the shaft's durability and performance. After resting half a day in the furnace, the ingot is retrieved for stauchen, or upsetting. Here, the crane reorients the shaft vertically, and the press compacts the shaft's structure further. The workpiece is then laid horizontally again for the second elongation process. Now, thousands of tons of pressure are applied to forge the steel into its final length and shape. Due to the extreme size and heat, the shaft must be supported during forging. A special forging crane and sometimes an auxiliary device called a schmiedegrä are used to stabilize and prevent sagging during processing. In the final shaping stages, any cracks detected are burned out using pure oxygen. At both ends of the shaft, excess material known as head and foot scrap is removed and recycled back into the melting furnace. Before final treatment, the shaft undergoes another heating phase. Then comes a crucial step: hardening in a massive water quench tank. The shaft, measuring up to 13 meters long and weighing over 80 tons, is submerged to lock in the required material properties. Finally, surface machining is carried out. Up to 14 centimeters of steel is removed with precision tools to achieve tolerances within 0.5 millimeters. This ensures the shaft meets exacting standards for its intended use. Saarschmied produces over 200 such generator and turbine shafts annually, destined for power plants and large marine engines. Each shaft costs on average €200,000, reflecting the complexity and precision involved in its manufacture. The assembly of the twist chair by Parata is a meticulous process, blending traditional Italian craftsmanship with modern precision. Each chair undergoes a carefully structured procedure to guarantee exceptional quality and durability. The process begins with testing and adjustment. At this stage, every wooden component is visually and manually inspected to identify any defects such as cracks, warping, or dimensional inaccuracies. The joints are trial assembled to ensure perfect alignment, with tolerances kept within 0.1 millimeters to maintain the high standards of Parata. Following inspection, artisans move to closing the gaps. Any slight openings between the parts are meticulously corrected by sanding or adding filler material. After adjustment, the allowable gap does not exceed 0.05 millimeters, ensuring the structural and aesthetic integrity of the chair. Next is the gluing phase, where a specialized wood adhesive with a minimum tensile strength of 10 megapascals is applied. The glue is carefully spread across all contact surfaces at a rate of approximately 0.2 milliliters per square centimeter to ensure a strong bond. Finally, the components are assembled and tightened using professional clamps. An even pressure of approximately 1.5 N per square millimeter is applied to secure the joints. The clamping is maintained for at least 30 minutes to allow the adhesive to reach initial bonding strength. Each twist chair is handcrafted in Parada's facility in Italy, primarily using premium woods such as Canaletta walnut and ash. The production process combines advanced machinery with the expertise of artisans who each have over 10 years of experience. It takes approximately 8 hours to complete the assembly of one chair, with at least 3 skilled workers involved, ensuring every piece embodies Parada's hallmark of excellence. At Best One Tools, the production process begins with sourcing CRV31 grade steel, ensuring high strength and corrosion resistance. Raw materials undergo initial inspection for thickness and composition consistency. Forging operations use automated hydraulic presses capable of applying forces up to 1,000 tons, shaping the tools with precise tolerances. Post-forging, tools are heat-treated at 850 degrees Celsius, followed by rapid quenching to achieve a hardness of 45 to 48 HRC. CNC machining operations, with a precision tolerance of plus or minus 0.01 millimeters, are used for shaping, drilling, and threading. Surface finishing includes polishing to a roughness average RA below 1.2 micrometers and applying anti-rust coatings. Every batch undergoes dimensional checks and mechanical strength testing as per ISO 9001 to 2015 standards. The plant, operated by more than 400 skilled workers, produces approximately 50,000 hand tools monthly, ensuring consistent quality and high performance for both domestic and international markets. The use of a 20-meter, 4,000-ton hydraulic press brake represents one of the most advanced solutions for bending extremely large and heavy steel plates, commonly required in shipbuilding, bridge construction, and heavy industrial equipment manufacturing. This article details the complete production process using this massive equipment, emphasizing precise operations, human-machine interaction, and key technical specifications. The process begins with material preparation. Steel plates selected for bending typically range in thickness from 20 millimeters to 50 millimeters and can reach up to 20 meters in length. Prior to any bending, each plate undergoes thorough inspection for flatness, surface defects, and material consistency. Plates must comply with strict tolerances to ensure the bending process achieves accurate results without introducing structural weaknesses. Once the material is approved, the machine setup phase begins. The hydraulic press brake, rated at a maximum bending force of 4,000 tons, approximately 39,200 kilonewtons, is carefully configured according to the plate dimensions and bending requirements. The effective working length of the machine spans 20 meters, making it capable of processing single, continuous steel sheets without the need for repositioning. Operators install the appropriate upper punches and lower dies onto the press brake. Tooling must be specifically designed to accommodate the material thickness and desired bend angles. Commonly, V-dies ranging from 100 mm to 250 mm opening width are used, depending on the plate thickness. The CNC, computer numerical control system integrated into the press brake, is then programmed. Parameters such as bend angle, bend length, material springback factor, and pressure force are inputted into the control software. Modern CNC systems allow for positioning accuracy within plus or minus 0.1 millimeters, crucial for achieving consistent bends across 20-meter plates. During the bending operation, the hydraulic rams apply synchronized pressure along the entire 20-meter working length. Due to the sheer size of the plate, multiple hydraulic cylinders, often between 10 to 14, are deployed along the ram to maintain even pressure distribution. This prevents material distortion and ensures uniform bending angles across the full width of the workpiece. Human operators play a critical role during setup and supervision. Typically, a team of 3 to 5 skilled technicians handles one bending operation. One CNC operator manages programming and machine control, while the remaining team members assist in plate alignment, clamping, and real-time monitoring. The bending cycle time varies depending on the complexity of the part and the number of bends required. For a simple single bend operation on a 20-meter steel plate, the cycle time generally ranges from 10 to 20 minutes, including material loading, alignment, bending, and unloading. After bending, each workpiece is carefully inspected. Dimensional verification is conducted using laser measuring systems or manual calipers for critical tolerances. Accepted dimensional deviations are usually within plus or minus 2 millimeters over the full 20-meter length. Surface inspections are also performed to identify any visible cracks, surface scratches, or die marks. If any adjustments are necessary, minor corrections can be applied through secondary low-pressure bending passes or manual correction processes, depending on the project specifications. Post-bending, the material may undergo additional surface treatments such as grinding or shot blasting to prepare for downstream operations like welding or painting. particularly if the final product will be used in critical structural applications. Safety measures are integral throughout the operation. The press brake is equipped with optical safety devices, pressure sensors, and emergency stops positioned along the operator walkway. All operators must wear PPE, personal protective equipment, including safety shoes, helmets, gloves, and eye protection. Lifting and material handling are assisted by overhead cranes, rated for at least 10 tons, to maneuver the heavy plates safely into position. Maintenance routines are rigorously followed to ensure machine longevity. Hydraulic systems are inspected weekly, die alignment is checked after every 50 cycles, and full system calibrations are conducted quarterly. Lubrication points across the press are serviced after every 100 operating hours. The integration of a 20M 4,000-ton hydraulic press brake allows manufacturers to produce large-scale, precision-bent steel structures with minimized material handling and maximum dimensional accuracy, supporting industries where structural integrity is critical. The production process of the MI4 involves 40 steps and 193 detailed procedures to transform high-grade steel into a premium smartphone frame. The process begins with precision pressing and cutting of the steel, followed by forging to create the desired shape. The steel is then CNC milled for high accuracy, ensuring perfect dimensions. After milling, the surface undergoes multiple rounds of fine polishing and sandblasting to achieve a smooth texture. The material is coated to enhance corrosion resistance and visual appeal. Further reinforcement steps ensure strength and durability. Throughout each stage, strict quality controls are applied to maintain exceptional standards. This meticulous process combines advanced machinery with skilled craftsmanship to deliver a flawless, aesthetically refined product that defines both strength and elegance. Fundição Metal Norte, located in São Gonçalo do Amarante, RN, operates in the precision casting of iron and steel components. The production process begins with mold preparation, using sand molds for complex geometries. Metal melting is conducted at controlled temperatures between 1,200 degrees Celsius and 1,500 degrees Celsius, depending on the specific alloy composition. The company employs electric arc or induction furnaces to ensure consistent heating. Each casting batch typically weighs between 50 kilograms and 3,000 kilograms, matching different industrial demands. After melting, molten metal is poured into molds at pouring temperatures averaging 1,400 degrees Celsius, ensuring optimal fluidity. Cooling and solidification times vary from 30 minutes to 5 hours, depending on casting size and thickness. Post-solidification, mechanical vibrators and shot blasting machines are used for mold removal and surface cleaning. Finishing processes include grinding with automated belt systems and CNC machining when tight tolerances below plus or minus 0.2 millimeters are required. Quality control is rigorous. Every batch undergoes ultrasonic testing, UT, for internal defects, and radiographic inspections, X-ray, on critical components. Metallurgical analysis ensures that hardness, tensile strength, and impact resistance comply with ISO and ASTM standards. Through precise control at each stage, Fundição Metal Norte produces durable and dimensionally accurate parts, supporting demanding sectors like mining, energy, and heavy machinery. ArcelorMittal Hamburg is one of Europe's leading producers of high-quality rolled wire, with an annual production volume of approximately 1 million tons. Founded in 1969, it was the first steel plant in Europe to combine an electric arc furnace, EAF, with a direct reduction facility, setting new standards in efficient and sustainable steelmaking. The production process starts with raw materials, sorted steel scrap and iron ore pellets. Scrap metal is stored in different grades and fed into the production cycle. Meanwhile, high-quality iron ore pellets are delivered and stored separately. Instead of traditional blast furnace processing, ArcelorMittal Hamburg uses a direct reduction method. Natural gas is heated to around 1,000 degrees Celsius, where it is split into carbon monoxide and hydrogen gases. These gases reduce iron oxide into nearly pure metallic iron, known as sponge iron, without melting the ore. This method significantly lowers energy consumption and carbon dioxide emissions compared to conventional methods. The produced sponge iron, along with steel scrap, is then melted in the EAF. The EAF at Hamburg consumes about 600 million kilowatt-hours of electricity annually. Graphite electrodes, capable of carrying up to 75,000 amperes, introduce intense electric arcs to melt the charge. The molten steel reaches temperatures around 1,630 degrees Celsius. A foaming slag forms during melting, which protects furnace walls from thermal stress. Sampling is performed automatically and analyzed by an optical emission spectrometer to fine-tune the chemical composition. Once the desired composition is achieved, molten steel is tapped into ladles, treated in ladle furnaces for temperature adjustment, and prepared for continuous casting. Steel is poured through a distributor into 6 copper-cooled molds. The resulting billets can be up to 16 meters long and weigh up to 2 tons. They are rapidly cooled through water spray systems and cut precisely to the required lengths. After cooling, billets are reheated to over 1,000 degrees Celsius in the rolling mill. The rolling process reduces the billet diameter from 55 millimeters down to as little as 5.5 millimeters. The wire rod achieves speeds of up to 100 meters per second during rolling. Finished wire rods are coiled into bundles weighing approximately 1.5 tons. Post-rolling, the coils are cooled under controlled conditions, ensuring uniform mechanical properties. They are bundled, barcoded for full traceability, and prepared for shipment. Each batch undergoes strict quality control measures according to DIN ISO 9001 for quality management and DIN ISO 14001 for environmental management. ArcelorMittal Hamburg operates a highly advanced and sustainable steel production process, combining direct reduced iron (DRI) technology with an electric arc furnace (EAF). Production begins with iron ore pellets, which undergo direct reduction at approximately 800 degrees Celsius using natural gas. This process converts iron ore into sponge iron (DRI) with a metallization degree of 95% and a carbon content of 2.3%. Without the need to melt the ore, significantly reducing energy consumption. The produced DRI is mixed with sorted steel scrap and melted in the EAF. This furnace achieves the necessary temperatures through high-power electric arcs, consuming less energy compared to traditional blast furnaces. The molten steel is then continuously cast into billets, ensuring uniformity and reducing material waste. After casting, the billets are cooled and transferred to the rolling mill. At the two-strand wire rod mill, billets are processed into wire rods with diameters ranging from 5.5 millimeters to 17 millimeters. The rolling mill operates at high speeds, maintaining excellent dimensional precision and surface quality. ArcelorMittal Hamburg is also preparing for a hydrogen-based future. The Hamburg H2 project plans to produce 100,000 tons of DRI annually using hydrogen, targeting a 40% reduction in carbon dioxide emissions compared to conventional processes. This modernization effort cements ArcelorMittal Hamburg's role as a leader in sustainable steel manufacturing. At Murayama Forging, the production of large S45C steel couplings is a meticulous and highly controlled process that showcases traditional Japanese free forging craftsmanship combined with modern precision. The process follows a strict series of steps designed to maximize material strength, dimensional accuracy, and surface quality. The process begins with material preparation. Large billets of S45C medium carbon steel, known for its excellent strength and machinability, are selected. Each billet is cut to a specific dimension based on the final size of the coupling to be produced. S45C is typically standardized to have a carbon content of approximately 0.42% minus 0.48% and tensile strengths ranging from 570 to 700 megapascals after heat treatment. The billets are heated uniformly in a gas-fired furnace to a forging temperature of around 1,200 degrees Celsius. This high temperature is necessary to soften the steel sufficiently for deformation while maintaining its structural integrity. Uniform heating ensures that the internal temperature of the billet matches the surface, minimizing internal stresses and potential defects during forging. The billet is removed from the furnace. Surface scale, which forms as a result of the billet's exposure to oxygen at high temperatures, is removed. This descaling is critical. Leftover scale can cause surface flaws or inclusions during forging. Descaling is performed using a combination of high-pressure air jets and mechanical scale breakers to achieve a clean, defect-free surface. The forming process officially begins. The billet is placed on a large, open-die hydraulic forging press, typically operating with forces exceeding 2,000 to 5,000 tons, depending on billet size and material. The operator carefully positions the billet under the press and executes controlled deformation strokes. The initial pressing flattens and spreads the billet to establish basic proportions. Skilled rotation and repositioning are essential to ensure even material flow, avoiding weak points or anisotropic grain structures. Shaping of the piece continues with precision. The operator repeatedly compresses and elongates the billet, controlling the forging ratio, the ratio of the initial to final cross-sectional area, to achieve desired mechanical properties. Typically, a minimum forging ratio of 3:1 is targeted for critical parts to refine grain structure and eliminate internal porosity. Murayama Forging places great emphasis on gradual and balanced deformation. This prevents internal cracking and ensures that fibers within the metal are properly aligned along the final geometry. Each stroke is planned to achieve gradual transitions without sharp edges or stress concentrations. The forging enters the critical adjustment phase. The piece's dimensions are refined. Operators monitor both the diameter and height, ensuring that tolerances are met precisely. In Murayama's operations, dimensional tolerances for large couplings are often held within plus or minus 1 millimeter. Multiple measurements are taken during this phase, using calipers and template gauges. If needed, slight reheating in the furnace may be performed to maintain optimal forging temperature during the final adjustments. The billet is removed from the furnace. Surface scale, which forms as a result of the billet's exposure to oxygen at high temperatures, is removed. This descaling is critical. Leftover scale can cause surface flaws or inclusions during forging. Descaling is performed using a combination of high-pressure air jets and mechanical scale breakers to achieve a clean, defect-free surface. The forming process officially begins. The billet is placed on a large open-die hydraulic forging press, typically operating with forces exceeding 2,000 to 5,000 tons, depending on billet size and material. The operator carefully positions the billet under the press and executes controlled deformation strokes. The initial pressing flattens and spreads the billet to establish basic proportions. Skilled rotation and repositioning are essential to ensure even material flow, avoiding weak points or anisotropic grain structures. Shaping of the piece continues with precision. The operator repeatedly compresses and elongates the billet, controlling the forging ratio, the ratio of the initial to final cross-sectional area, to achieve desired mechanical properties. Typically, a minimum forging ratio of 3:1 is targeted for critical parts to refine grain structure and eliminate internal porosity. Murayama forging places great emphasis on gradual and balanced deformation. This prevents internal cracking and ensures that fibers within the metal are properly aligned along the final geometry. Each stroke is planned to achieve gradual transitions without sharp edges or stress concentrations. The forging enters the critical adjustment phase. The piece's dimensions are refined. Operators monitor both the diameter and height, ensuring that tolerances are met precisely. In Murayama's operations, dimensional tolerances for large couplings are often held within plus or minus 1 millimeter. Multiple measurements are taken during this phase using calipers and template gauges. If needed, slight reheating in the furnace may be performed to maintain optimal forging temperature during the final adjustments. The final height adjustment is conducted. This step ensures that the coupling achieves exact specifications for fit-up and performance in its final application. It's common to see adjustments made with very light press forces at this stage, ensuring minimal overworking or strain on the material. After final forging, the component is left to cool slowly in controlled conditions. Typically, the cooling is performed in insulated boxes or under still air to prevent rapid quenching, which could introduce thermal stresses and potential cracking. Targeted cooling rates for large steel forgings are often around 50 to 100 degrees Celsius per hour, depending on the steel grade and section thickness. Once cooled to handling temperatures, the forging undergoes initial inspections. Surface quality is checked visually, ensuring no cracks, laps, or scale remnants are present. Dimensional checks are repeated with precise instruments. Subsequent processes may include heat treatment. To achieve the required hardness and toughness, the coupling may undergo normalization or quenching and tempering. S45C typically reaches hardness levels around 200 to 240 HB after normalization. Rough machining. Machining operations define critical surfaces while leaving extra material for final finishing. Final inspection. Ultrasonic testing, UT, and magnetic particle inspection, MPI, may be used to detect internal or surface flaws not visible to the naked eye. Murayama Forging's commitment to quality ensures that every coupling manufactured delivers the required mechanical properties and dimensional accuracy for demanding industrial applications, such as shipbuilding, power generation, and heavy machinery. The meticulous free-forging process at Murayama is a testament to the balance between traditional craftsmanship and modern manufacturing precision, producing components that meet strict performance and safety standards, all starting from a glowing piece of heated steel and skilled human hands. At Yanakive Iron and Steelworks, slag handling is a vital part of the production process. During steelmaking in BOF furnaces, slag is separated using monocon manipulators, improving steel quality and furnace efficiency. The hot slag is transported by specialized trucks to cooling sites, where it is either air-cooled or water-quenched. Once stabilized, the slag undergoes further processing for reuse. Approximately 20% of processed slag is used in road construction, 42% in cement manufacturing, and 19% for mine backfilling. Environmental investments exceed $200 million, including installing new sinter plants and gas cleaning systems that reduce dust emissions below 10 milligrams per cubic meter. Water discharge has been reduced by 648,000 cubic meters annually into the Bolivian River. These measures help Yanakiev achieve significant environmental and economic benefits through advanced slag recycling technologies.